In today's video, we're going to be talking about graphing with asymptotes, and specifically in calculus. You've probably heard of asymptotes in Algebra 1, Algebra 2, maybe pre-calculus. And as a quick review, let's talk about what these asymptotes are. An asymptote is basically a place where a graph cannot cross. It could appear on one side, it could appear on the other side, but it cannot cross over like that. That is not allowed. That doesn't work if there's an asymptote in the way. Basically, the graph cannot equal whatever that vertical asymptote's point is at that specific point. A horizontal asymptote is a point on the y-axis that our graph cannot equal and cannot cross, and a vertical asymptote is a point on the x-axis where our graph cannot equal and cannot cross. We can actually figure out where horizontal and vertical asymptotes exist on a graph using limits, so let's talk about it. First of all, vertical asymptotes exist whenever x is approaching a finite number for a function, and that limit ends up equaling positive or negative infinity. As an example, if we have the limit as x approaches 0, a finite number, of 1 divided by x, we get 1 divided by 0. And as x gets closer and closer to equaling 0, 1 is being divided by a smaller and smaller number. In other words, this number keeps growing exponentially until it reaches 0. So this number is basically infinity. Similarly, we have a horizontal asymptote whenever the limit as x approaches infinity of a function is equal to L, aka a finite number. L could be any number. So as a very similar example, if we have the limit as x approaches infinity of 1 divided by x, if we plug in infinity for our limit, we get 1 divided by infinity. And well, dividing a finite number by an infinitely large number is basically 0. So as you can see here, when x approaches infinity, we end up getting a finite number, which means that there is a horizontal asymptote somewhere on the function, and we need to figure out what it is. Let's do an example to figure out how to use these vertical and horizontal asymptote problems to our advantage. In this example, we need to find the limit as x approaches infinity of the function 3x squared minus x divided by 2x squared plus 1. If we were to just plug in infinity here, we would end up getting 3 times infinity squared minus infinity divided by 2 times infinity squared plus 1. And this is equal to the indeterminate form of infinity over infinity. And I forgot to mention earlier, if x approaches infinity of some function and either equals a finite number or an indeterminate form, then there is a horizontal asymptote. In this case, we reach one of those indeterminate forms. By the way, the indeterminate form is something like infinity over infinity, or 0 divided by 0, where essentially we don't really know what this equals. How do you divide an infinitely large number by another infinitely large number? After all, infinity is a concept, not an actual number, so we don't really know what's going on there. It's the same thing for 0 divided by 0. How do you take 0 things and divide it into 0 groups? It's indeterminate. We don't really know. But what that does tell us is that we need to do something algebraically to manipulate our original function in order to get it into a form where we could determine its limit. So let's do that now. So you may notice that the highest power of both x's within this limit is x squared. It is the highest exponent that we have within this function. We kind of want to get rid of that to some extent, because if we keep multiplying these finite numbers by infinity, it's just going to equal infinity. So let's take this function and move it down here. 3x squared minus x divided by 2x squared plus 1. And what I'm going to do is I'm going to multiply it by 1 divided by x squared on top and bottom. Distributing this to every number, this function ends up equaling 3x squared times x squared. Remember, whenever we multiply by a fraction, whatever is here, it turns into our numerator, and whatever's on bottom turns into our denominator, minus x divided by x squared, all divided by 2x squared divided by x squared plus 1 divided by x squared. Now, obviously, we can simplify this down a little bit. First of all these x squareds will cancel out, and one of these x's and this x will cancel out. So our new function turns into 3 minus 1 divided by x divided by 2 plus 1 over x squared. So let's now plug this back into our limit like we had before. The limit as x approaches infinity of this number. Well, if we were to plug in infinity, 1 divided by an infinitely large number is basically 0. So this goes away. And similarly, 1 divided by an infinitely large number squared is most certainly 0. So then this limit just turns into 3 halves. And that is not only our limit, but also our horizontal asymptote, denoted by HA. Now you may have noticed that this horizontal asymptote just turned into the leading coefficients of both of these highest power numbers. And we're going to talk about that in just a second here. But this is how you'd solve a problem whenever x approaches infinity, you get either an indeterminate form or a finite number, even though you approached infinity. It may take a little bit of tricky algebra, but once you figure it out, it really gets pretty easy. And in fact, I'm about to show you a trick where you don't even have to do any of this algebra. Let's talk about the Tower of Power. So I'm going to start writing down what the Tower of Power is. And once I'm done, I'll explain why I wrote it in that order and what its significance is. So at the top of our Tower of Power, we have x to the x power. Then we have x factorial, followed by 3 to the x power. Then right below that is e to the x. Now the reason that this 3 to the x is above e to the x is because e is actually equal to 2.72, not repeating onward. So 3 is technically slightly bigger. Then we have x to the 100th power, and right below it is x squared. Similarly to how e to the x is slightly smaller than 3, x squared is smaller than x to the 100th. So once you go up the Tower of Power, that just means you have a higher exponent. Then we have x, then we have the square root of x, then we have the fourth root of x, fourth root, like that. And then all the way at the bottom of our Tower of Power is natural log of x. So what's going on here, and why is this Tower of Power significant? Well, whenever we have a function where we have one function being divided by another, we can use these in order to find our horizontal asymptotes much more easily. So remember in our last problem, whenever we had 3x squared minus x divided by 2x squared plus 1, well, you may remember that this limit ended up equaling 3 halves. But why did it equal 3 halves? Well, according to the Tower of Power, first of all, we don't care about anything that's lower than our highest power. We have 3x squared and 2x squared. And if we were to plug in infinity for 3x squared and 2x squared, plugging that in for x of course, ultimately these numbers get infinitely big. But we also know that there is something going on as this reaches an indeterminate form. What the Tower of Power tells us is that all of these numbers will eventually approach infinity if we were to plug in infinity for x. The ones at the top approach infinity the fastest, and the ones at the bottom approach infinity the slowest. So for example, if you have something like x to the x power divided by natural log of x, the limit of this function would just end up being infinity. And that's because this x to the x power approaches infinity way faster than natural log of x. But if we were to flip it, if we had natural log of x divided by x to the x power, and that approached infinity, this limit would just equal 0. Because natural log of x approaches infinity way slower than x to the x power. So basically be a much smaller number divided by an infinitely large number, which as we talked about earlier is essentially 0. Similarly, this would be massive infinity, I should say, divided by a much smaller infinity. So it would just eventually be infinity, similar to how 1 divided by 0 ends up being infinity as the limit. So this Tower of Power can actually help us solve these kinds of problems way faster without any of the algebra. In this scenario, our leading powers are the same. So if you want to find the horizontal asymptote, you just take their coefficients and divide them, which of course in this case just equals 3 halves. So anyways, it may not be a bad idea to memorize the Tower of Power. It could come in handy whenever we're talking about graphing within calculus. We're going to do one example problem where we put together the first derivative test, the second derivative test, and the stuff we learned in this video in order to make a graph that has a function with asymptotes in it. So let's do that now. In our example, we want to graph the function 4x minus 2 divided by x minus 3. The first thing we're going to find is the vertical and horizontal asymptotes because, well, that's what we've been doing this whole video. So let's first do the vertical asymptote because if you ask me, it's much easier. Now, one of the strategies I mentioned early in this video is that if our denominator ends up equaling 0, we have a vertical asymptote somewhere. So what number minus 3 would equal 0 on the bottom in order to give us a vertical asymptote? That's right, if we were to put 3 in here at the bottom, x equals 3, then we get 3 minus 3, which would equal 0, therefore giving us a vertical asymptote. And this is the only one in our problem. So the vertical asymptote here is at 3. So let's denote that over here. Here we have this dotted line, which is our asymptote, and this is x equals 3. There's our vertical asymptote. Now our horizontal asymptote is slightly trickier, but still not too bad. We just talked about Tower of Power and how that can help us find horizontal asymptotes much more easily. Well, you may notice that we have x, and we have a coefficient of 4 and a coefficient of 1 attached to those x values. Since the x values are of the same power in the Tower of Power, we just need to divide their coefficients to figure out what the asymptote or the limit of this function would be. So we just get 4 divided by 1, which of course is just equal to 4. So there's a horizontal asymptote at 4, or y equals 4 specifically. So we denote that there, looks something like that. Here is 4 on our graph. All right, that wasn't so bad. Now we need to do everything else from the first and second derivative test in order to draw an accurate graph. So first, let's figure out where this graph is increasing or decreasing. In order to do that, we need to use the first derivative test and use a sign chart. Now, I won't lie, the derivative of this function is kind of a pain in the butt, so I'll just give it to you here. F prime of x is equal to -10 divided by x minus 3 squared. Now, as you may remember from the first derivative test, we need to draw a sign chart to figure out where this function is increasing and where it's decreasing. And we also need to find our critical points in order to figure out what numbers to plug into our function to figure out where it's increasing and decreasing. Let's do that with a sign chart. Let's just draw our sign chart here. And the only critical point that we have to worry about is 3. Remember, that's an asymptote. Whenever we plugged in x minus 3, we got an undefined function. So our only critical point in this is 3. And remember, we don't need to worry about 4 as a critical point because all of our critical points are only within the domain, which are only x values. So now let's plug in one number below 3, say 2. We would get -10 divided by 2 minus 3. Oh, hold on, I wrote that backwards, my bad. 2 minus 3 squared. Now this function would end up turning into -10 divided by -1 squared. A negative number squared will always be a positive number. So this ends up being a negative number divided by a positive number, which is a negative number. So below 3, this graph is decreasing. Now let's plug in a number slightly above 3, say 4. So let's do that here. We get -10. -10 divided by 4 minus 3 squared. So once again, we have 4 minus 3 equaling 1. 1 squared, of course, is just 1. So we end up having a negative number divided by a positive number, which again is negative. So this graph is literally decreasing everywhere. We don't have to worry about that. So let's use interval notation to talk about where this graph is increasing and decreasing. So this graph is decreasing anything from 3 down to -infinity. So from -infinity to 3. Now we can't include 3 because of course we have this vertical asymptote here. Can't include it. So we're going to draw this union sign here. And then this graph is continuing to decrease from 3 to infinity. So from 3 to infinity. And there we go. Now we know where this graph is increasing and decreasing. Next, we need to find the concavity of this function, whether it's concave up or concave down. And as a quick review, a function is concave up if the function can hold water at that area. If the function is concave down, if water would just spill over. And we can use the second derivative test to figure out where this function is concave up and down. So let's do that now using the second derivative test. First, we need to find the second derivative of our function here. And once again, we can do it, but I really just don't want to do the quotient rule right now. So I'll just give you the second derivative. The second derivative of 4x minus 2 divided by x minus 3 is equal to 20 divided by x minus 3 cubed. So once again, in order to figure out where this function is concave up and down, we should use a sign chart, just like we did in the second derivative test. In case you don't know how to do the first and second derivative test, by the way, I have a video on that. You can click the link up in the top right corner. So let's draw our sign chart down here. And remember, we just need to check on either sides of our critical points, but our only critical point is just 3. So once again, we only have to check one number above 3 and one number below 3 to see what the graph is doing below and above our critical point. First, let's plug in a number below 3, our critical point. So once again, we'll plug in 2. So this will equal 20 divided by 2 minus 3 cubed. This will end up equaling 20 divided by -1 cubed. And the interesting thing about cubing a number is, unlike squaring a number, it doesn't change the sign. So this ends up being 20 divided by -1 cubed, which is -1. And this ends up being a negative number. So everything less than 3 is concave down. Now let's do a number slightly higher than 3, say 4, just like we did last time. So we're going to do 20 divided by 4 minus 3 cubed. Similarly, we have 4 minus 3 equaling 1 instead of -1. 1 cubed, of course, is just 1, as the sign doesn't change, and 1 cubed is just itself times itself 3 times. A positive 20 divided by a positive 1 is a positive number. So above 3, our function is concave up. So let's denote that here on our little chart here. Our function is concave down from 3 down to -infinity. So -infinity to 3. And remember, we can't include 3 because of the vertical asymptote over here. And this function is concave up from 3. Once again, can't include 3 because of the asymptote. To infinity. Not so bad, right? Now we know how this function faces, either downward or upward, holding water or dripping water, one of the two. And actually, just with this information, we can graph our function. Now you may be saying, hey, how can we graph this function? We don't have our extreme points. We don't have our inflection points. And to that I say, these asymptotes remove the need to do that. Now usually we would have an inflection point at the critical point 3, but here's the thing. This function has an asymptote at 3, therefore it doesn't exist at 3. Therefore, the only place where there could be an inflection point the function cannot exist. So there is no inflection points in this graph. The other nice thing is that since our only critical point is also a vertical asymptote, it also can't be an extreme point, also known as a relative maximum or minimum, because it doesn't exist there in the first place. So just using this information, we can draw our graph. And our graph is going to look something like this. As our function gets closer to to 4, it approaches negative infinity, and as our function approaches 3, it approaches negative infinity. So it looks something like this on this inside part. And remember, we determined that this is concave down, so we know that it is facing this way, where the water would spill out if you tried to dump water on top of it. Now, on the top of our graph, we would have something like this. Whereas x approaches 4, our function approaches positive infinity way over there. And as our function approaches the asymptote of 3, our function approaches infinity. And it's concave up because we determined that here with the second derivative test. If you were to spill water here, it would hold the water right there. And just by using limits and a couple of different derivative tests, we were able to draw a graph just by using the first derivative test, the second derivative test, and a couple things to check for asymptotes. And that's all I have for you guys today. I hope you enjoyed this lesson and consider subscribing if you liked it. If you need more Calculus 1 lessons or are ready to learn more, check out my Calculus 1 playlist linked here. I'll see you guys in the next video.